Alright, welcome to APNIC e-learning web class. We'll be doing IPv6 addressing and subnetting. So in this section, IPv6 addressing and subnetting, we'll discuss mostly about IPv6 address, how it is structured, how we represent IPv6 address, and how you do subnettings and all sort of other stuff. To understand IPv6 subnetting, obviously you need to have the basic understanding of binary mathematics. So if you have a clear knowledge of binary mathematics, it will be easy for you to sort of follow this presentation. And also throughout the presentation, if you have any question, you can ask your question anytime. You don't need to wait till the end of the presentation. Just write your question on the chat box and I'll try to answer your question as quickly as I can. All right, let's move on. My name is Nurul Islam Roman. I am the senior training specialist now in APNIC. I'm in APNIC since 2006. So when I joined in APNIC, I used to be the host master, and that time I distribute addresses to our members. Then I moved into the learning and development team and doing training for our members, trying to transfer my industry knowledge, experience to our member engineers so that it will help them to build and operate internet effectively. And also, as housekeeping stuff, we have an URL called www.apnic.net/e-learning-support. On that URL, we try to outline the common problem that you might face when you are using this e-learning web class, the platform. It's worth having a look to sort of troubleshoot your basic problem if you have any. Okay. And also, when we will finish the presentation, I will show you an URL. You can use that URL to give us some feedback, and your feedback is very important for us because this is how we will try to update or improve our future e-learning session. Okay. All right, IPv6 addressing. So initially, IPv6 address, people have got some scare about it. I would say scare because this whole 128-bit address looks very messy, right? So we'll try to sort of give you a very well structured approach so that it will be easy for you to understand IPv6 address, because this address is very important in your IPv6 deployment and planning. So whole IPv6 address is 128-bit, right? So since it is 128-bit, so how many number of addresses it can generate? Simple mathematics, 2 raised to 128. That will give you very big numbers. Like this is the big number in decimal. Like you see, I can't even read this. This is too big. So for a computer, this 128-bit address, they will deal with binary, so that's easy for them. But as a human being, when we need to do planning with the address, that makes things really tedious, right? It's very difficult job for us. So that is why we need to find out a way to make it short and sweet, and it will be easy for us to deal with the number. How we can do that? So that is why the whole 128-bit address we can represent in a very meaningful way. So if we go and try to find the best option to represent that IPv6 address, we have 3 options. So binary, hexadecimal, and decimal. Binary is too big. Decimal is still too big. It takes 39 digits to represent the whole number. And then last option is hexadecimal. In hexadecimal, how we can do that? The whole 128 binary bit, if we represent into hexadecimal, that will take 32 hexadecimal digits, right? So one hexadecimal digit actually will contain 4 binary bits. So that is what we call nibble bit boundary, right? So 128 binary bit will be represented by 32 hexadecimal digit. So each hexadecimal digit will contain 4 binary bit, and that is what we call nibble bit boundary. If we try to see the representation system of the whole 128-bit, as I said, that will be represented into hexadecimal, so 32 hexadecimal digit, but still 32 hexadecimal digit is too big. So that is why we create groups, or we call blocks, right? So 4 hexadecimal digit, we can create one block. So if we take 4 hexadecimal digit into one block, then from 32 hexadecimal digit, we easily can create 8 blocks. So that is how in IPv6 address we have 8 blocks, and each block will contain 4 hexadecimal digit. And when we represent it, each block will be separated by a colon. That's what the representation of IPv6 address. If you see 1, 2, 3, 4, 5, 6, 7, 8 blocks, and each blocks are separated by a colon. All right. Then still it is too big, so we need to have a system to abbreviate it, right? So what are the abbreviation rules to make it short and sweet? So there are 3 abbreviation rules. Number 1 rule is, if any of the block out of 8 block, if any of the block is starting with 0, that 0 we easily can abbreviate and then just write the numbers without zeros. So for example, in block 2, what we have 2 0 and then 2 3, 0 0 2 3. So those are the 2 leading zeros. So when we need to abbreviate those leading 2 zeros, what we can do, that we can write those things in this way, 23, just 2 3. Then where are those 2 zeros gone? It's just abbreviated on the representation. But when it goes to the computer, your computer knows on that block there are 2 zeros missing, and they can retrieve those from the beginning of the block. That's what we call leading zeros. This is what abbreviation rule number 1. Then we have abbreviation rule number 2. What is that? Rule number 2 is, on any of the block, if there are continuous zeros, like on block 3, all are zeros, right? So if there are continuous zeros, then we can abbreviate those with a single zero. You see that's how we abbreviate it. So that can be done. It's option 2. And then option 3 is, if there are continuous zeros, if you see the block 3, 4 and 5, all are continuous 0, those all continuous 0 block can be collapsed into a double column. Then all those 0 blocks are missing, right? So how many blocks we have now after abbreviation? 1, 2, 3, 4, 5 blocks. Out of 8, we have only 5 blocks. And how many blocks are missing? 3 blocks are missing. Where are those missing blocks? Are inside the double column. That's it. So this is how we can abbreviate it. So if we abbreviate our IPv6 address in that way, we can make it very short and sweet. Okay. Is it all clear? Abbreviation rule, how we can abbreviate IPv6 address? Is there any question by any chance? If not, then we can move on. So now if we see the IPv6 address, that is how we represent the whole IPv6 address in 8 blocks. So for an example, if you take an example address like 2010BB8:DEAD:1AB6:503F:A804:71D9. So all 8 blocks, we can convert them into binary. So this is what the equivalent binary is. So 2 will become 0010, 0 will become 0, 0 will become 0, and then 1 will become 0001. So this is how the whole hexadecimal representation of IPv6 address can be converted into binary, and it's too big, so big. So that's what an example of IPv6 address in binary and then equivalent hexadecimal. Okay. Okay, so out of the whole 128-bit, you saw how we can represent it. Now we'll talk about the addressing structure. So whole 128-bit IPv6 address, that actually divided into 2 equal parts, right? On the left we have our network prefix part. On the right we have our interface ID part. So what is the network prefix? Network prefix part is the part that we use for the global routing, right? And interface ID is actually used for the interface ID. I mean, as a host address. Let's have a look on the further detail of network prefix. So in network prefix, out of the 64-bit, first 3 bits in binary actually allocated for or reserved for Unicast operation or or unicast function. So that is why if you see first 3 bit, so IPv6 unicast address start from 2000:/3. So from board bit 4 up to bit 12, which is actually 9 bit used for further subnetting on the central registry level. So on the central registry level, what they do, they take 9 bit from bit 4 up to bit 12. So 2 to the power 9 equal to 512 number of /12 they can create as a subnet, right? So out of the 512 number of /12, they have distributed 5/12 to the 5 regional internet registry in the world, right? And then they keep 1/12 for the special purpose. So this is how in each regional registry they receive a /12. So what the registry, as an example, APNIC, they do, or the registry that does, they create further subnet from that /12. So if you see APNIC /12, APNIC can create up to bit 32, right, which is 20 bit more from 12 bit, or up to /48. So in a situation where APNIC is giving address to an ISP or as a service provider, APNIC normally gives them a /32. When the address is given to an enterprise, APNIC usually gives them a /48. So as a service provider, when you receive a /32, then how many bit you have to do your subnetting? Only 32 bit to do your subnetting, because your network prefix part ends on bit 64 in here, right? So as a service provider, you receive a 32, then you have 32 bit to do your further subnets. On the other hand, if you're an enterprise will receive a /48, right? So when enterprise they receive a /48, they have got how many bit to do their plan? So they have got another 16 bit to do their planning, right? So this is how on the service provider level or on the enterprise level, they can do the plan. Service provider can do plan on 32 bit, enterprise can do plan on /48 bit. That is what the normal situation. But if in your case, if you need more than that as a service provider, you can get more than that, more than /32. Or as an enterprise, you can get more than /48 if you can justify, right? But normally as a default, you'll get a /32 ISP allocation and /48 enterprise assignment. Is there any question? No? Okay, I hear you. Probably you might have some issues. Okay, good. Good to know that you can hear me now. All right, so then we have end-site subnets. What is end-site subnets? For example, when we give address to our LAN on the end side, the concept is, as a best practice, you give /64, right? I'll give an example. If you have a physical network into an office, and on the physical network, if you have like 200 machine, out of 200 machine or computer, you have got like 10 computer for the sales, 20 computer for the accounts, and probably 30 computer for the engineering departments, right? This is how you have a number of computers into your LAN. So what you do in IPv4, so based on the number of computers that you have in each segment, you create small VLAN, right? So when you create small VLAN from a physical network, physical LAN, we have a small virtual LAN, and in each virtual LAN, we give IPv4 prefix based on the number of hosts they have, and based on that, we give prefix /27, /25, /26. It depends on number of hosts. That's what the concept in IPv4. But in IPv6, concept is a bit different. How it is different? In IPv6, per end site it is recommended to give /64. It means per VLAN /64. Doesn't matter how many computers you have in each VLAN, but each VLAN just gives /64. It's very fixed. It's not variable as IPv4. That's recommended. You can violate this rule, but this is what recommended /64 per VLAN. Then when you give /64 per VLAN, then from that, within that VLAN, if you have a number of hosts or a computer, they will build their host address, which is the interface ID, either from their MAC address or even by statically, right? So yeah, if you use MAC address, that's what we call auto configuration. stateless auto configuration, or there are a number of options to build the last 64-bit interface ID. So this is what sort of a structure of IPv6 address. Is there any question from that addressing structure, by the way? Because this slide is very important in your planning. When you need to do your plan, this slide is very important. Now, this is how you should do the plan into your network. No question? Or we'll move on. Okay, so if you see the IPv6 address management hierarchy, how address has been allocated, as I said, APNIC make allocation of /32 by default in IPv6, right? So when someone is a service provider, they'll receive a /32 from APNIC, and APNIC make /48 assignment as an enterprise. That's by default. So how these addresses APNIC distribute? When APNIC receive address from the central registry, for example IANA, as I said, APNIC receive address on /12-bit boundary. When APNIC receive on /12-bit boundary, from there APNIC give their member as a /32 allocation or /48 assignment. Both the case /32 allocation or /48 assignment, those will be portable. It means member can carry with them. Sub allocation. So when member, they will give address to their downstream customer or the downstream network, right? So they give normally /40 /64 is up to their planning, up to their policy. If the members downstream organization is another small ISP, probably member can do sub allocation, right? Or if the member downstream customer is an end user, they can do assignment, right? But both the case, sub allocation or assignment, it will be non-portable. Okay. Now we'll see the IPv6 addressing model. What are the models we have? We have unicast, we have anycast, and we have multicast. What is unicast, what is anycast, and what is multicast? Unicast, as a definition, if you see, unicast transmission is on the packet. If the packet source is unique address, packet destination address is unique address, right? Then what will happen? When source machine will create the packet, they will add packet source IP address as a source address, and the destination machine's IP address as a destination address. So when that packet goes, the packet will go to the destination machine only. So the transmission is one-to-one, and in terms of IP packet, source address is unique, destination address is also unique. Then we have anycast and multicast in IPv6. What is multicast? First we have a look on the multicast. Multicast transmission is when the source machine create a packet, single packet, right? Not a stream of packet, just a single packet. And on that packet, if the source address is a unique address and destination address is a group address, right? Not a unique address in in unicast. So in multicast, destination address is a group address. So when that packet created, who will receive the packet? A number of machines who belongs to that group. Normally in multicast scenario, 10, 20, 2,000, 5,000 machines that belongs to the same group. So when they belong to the same group, every individual machine will receive a copy of the packet. If 5,000 machine belongs to that group, then 5,000 machine will receive 5,000 individual copy of it. But source machine will create only one packet, right? And that packet will be copied to all the members of the group. So that's what we call multicast. And anycast, in anycast, same concept. Source address is a unique address in the packet, and destination address is also a group address. But the difference between multicast and anycast is in anycast, the packet will be delivered to the nearest computer of the source, right? On the diagram, if this machine, source is in here, the nearest computer is this one. Then who will receive the packet? Only this guy will receive the packet, but other two guys who are far from the source machine, they will not receive the packet. So the difference between anycast and multicast is, in anycast, only one machine will receive the copy of the packet, right? Rest of the other machine will not receive any copy, who are the far machine, who are far from the source. But in multicast, every machine will receive a copy of the packet. And here, so that's the transmission type that we have, or addressing model that we have in IPv6. And as we explained, in IPv6, there is no broadcast. No broadcast in IPv6. All the broadcast function in IPv6 are done using multicast. We'll see some special address in IPv6. Loopback address, which is :1/128. In IPv4, the loopback address is 127.0.0.1. Unspecified address in IPv6, which is :/128. There are two special addresses in IPv6, which is IPv4 mapped IPv6 address. If you need to map your IPv4 address with an IPv6 address, if you are building a dual stack machine, then this is how you can map it. 96-bit, there will be a predefined standard or predefined pattern, which is this, and then after that 32-bit IPv4 address, convert it to binary and put it there and convert it back to hexadecimal. That's what will be your IPv4 mapped IPv6 address. And what is IPv4 compatible IPv6 address? Compatible IPv6 address is just 96-bit and then your IPv6 address at the IPv4 address, 32-bit v4 address at the end. The compatible v4 address is sometimes used if you are building a dual stack machine, or sorry, if you are running a daemon that support only IPv6 but running on a dual stack machine, right? So that can generate an error message. So that's why to be compatible with a dual stack machine and IPv6 supported only daemon, you can use this sort of compatible address. Right, that's the thing probably programmers they need to look into. IPv6 address range, unspecified address, :/128, loopback, :1/128, global unicast 2000:3, link local address FE80::10, and multicast address FF00::8, and ULA prefix is FC00::7. So that's what the range of addresses that we have. So ULA prefix is sort of a prefix that is used as a private address in IPv6. Now we'll see the link local address. What is link local address? Link local address in IPv6 is a special type of address that is only used to communicate within the LAN. If you can remember, like in Windows and IPv4, if there is no DHCP v4 server, no static address on the machine, if you build your machine or if you switch on your machine, then your machine will try to discover the DHCP servers. If there is no DHCP server, then what your machine will do, they'll come up with a address which start with 169, right, in IPv4. So this is what sort of an example of link local, right? So that address can be used within the LAN, but that didn't have any standard. Only Microsoft tried that way. But in IPv6, it becomes a standard. Every IPv6 supported host, they'll build a link local address, and that start with FE80, right? So that link local address will start with FE80, and if you just switch on your computer and connect to the network, then your machine will have a link local address. That network prefix start with FE80, and then from their MAC address, if you use UI64 or any other algorithm, they build their interface ID, and rest of the bit they'll pad up with 00 on the network prefix side. Okay, so this is how link local address. The specialty of link local address is if you create any packet source as a link local, destination as a link local, that packet will never cross a router. So you cannot send a packet or link local packet across the router. Okay. Okay. Local address with network prefix. So this is what the ULA prefix. So if you need to connect our network from one side to the other side through a router, so for example, your point-to-point side from X city to Y city, right? Then we need to use the router to connect them. So when you connect to network using a router, then we use a special address called ULA address, and using ULA address, you can connect two networks through a router, right? So that's what sort of a private address in IPv4. But the difference of IPv4 private address and IPv6 ULA prefix is, in IPv4, there is a fair chance of a duplication of address. So for example, organization X, they build two sites, so they use two random numbers to build their two sites. And organization Y, they also probably use the same range. As long as both the organizations are connected, that's fine, no issues. But what if they merge together? Then there will be a problem. Either X or Y organization they need to renumber their network, right? But in IPv6, if we use ULA prefix for that, that will give little bit of better option. How it is little bit of better? Using ULA prefix, if you build your site address, which is /48, we use a pseudorandom algorithm. So by using the pseudorandom algorithm, if you build your site address, right, there is a fair chance you'll have a unique address, even though in between two organizations. It's a mathematics, right? So if you use pseudorandom algorithm and start building your site address, all the organizations in the world, they'll have nearly unique site address. So if they merge together, there is a very, very unlikely case, or very, very sort of low possibility of duplication. A global address with network prefix. So in IPv6, if you see the global address, that range start 2000:3 and end with 3000:3. That's the global range. And from that range, APNIC is given 2406:2000:12. Same way, ARIN, APNIC, LACNIC, and RIPE also given their own prefix range /12, right? And for 624, there is a special address which is 202:16, but that is deprecated already. So you don't need to worry about that 624 address anymore. For documentation, an example, there is a special prefix. For documentation, we have a prefix 2001:0db8:/32. For example, we have a special prefix called 3FFF:/32, right? So when you are writing books, white papers, journals, you use this prefix for your documentation and example. Now you'll see last 64-bit interface ID. The last 64 interface ID, right? How it can be generated. As I said, the very popular option is EUI64, right? So how EUI64 works? They take 48-bit MAC address from the LAN card, right? And there's a way to build. I'll show you in the next slide. Then what are the other options? You can provide the interface ID from a DHCP basic server, or you can use a manual or static configuration, or you can use another algorithm called pseudorandom algorithm. They automatically generate the last 64-bit of interface ID, and probably possibly in future you can have more options for that. Okay, let's have a look EUI64 algorithm, how it works. In EUI64 algorithm, the whole 48-bit MAC address we divided into two parts, /48 in this side, sorry, /24 in this side, which is OUI part, and /25 and another 24-bit on this side, which is our organizational specific serial numbers. So in between, we can add FFFE. So when we pad up FFFE in the middle, then 24, 16, 24. Altogether, it will become 64-bit interface ID. So when you generate from a physical address, when you generate an interface ID from a physical address, right? It's a convention in IEEE. If any address is physically burned on the LAN card, your 7-bit flag bit will always be 0, right? So the convention is from a burned-in address, if we generate an in address, so to set a flag for generated address, it will be 7-bit will be 1. So that's why since we are generating an address, so we change the 7-bit to 1. This is how our EUI64 algorithm works, and this is how you can generate interface ID. Okay. Zone ID, which is a very important thing to troubleshoot. So in your computer, normally nowadays we have at least two interface cards. One is the wireless interface and one is our LAN interface, right? So when you have two interfaces on a machine and both the interfaces are active, then you can see both the interfaces are sharing the same subnet, so FE80, in link local. So that is sort of a violation of the routing policy, because both interfaces cannot share the same subnet. So that is why within the machine only, to identify each link, we have a zone index. This is how, and that you don't need to do it. Your OS will automatically build a zone index, right, to identify those two interfaces separately. So what you need to remember is when you are pinging from your machine, which LAN card you are using on your machine, just specify that zone. That's it. Then your ping packet will take that specific interface to go out, right? So in Microsoft implementation, they use percent and then unique number. Mac, they use percent en0, en1 based on the interface name, right? Different ways handle it differently. IPv6 auto-configuration, how auto-configuration function works. As I said, from that 48-bit MAC address, they can generate their interface ID, right? Or they can use any other algorithm to generate the interface ID. But in general, if we classify in IPv6, we have two mechanisms, stateless and stateful. So auto-configuration belongs to the stateless, because in that situation, as an administrator, I don't have any control what the interface ID will be, because it will be generated automatically. On the other hand, stateful mechanism is DHCPv6 or static, right? In the DHCPv6 or static, as an administrator, we have a control of what address they will come up with. So if we see auto-configuration functions, how it works. So new machine, this green machine, when you just switch it on and try to come into the network, what it will do, it will try to build is link local address from the MAC address and US64. This is the algorithm, right? And that is what is to be used address. So when he is planning to use that link local address, right? So he will do a sort of check on the network whether this address has been used already or not, just to make sure, like, there is no address duplication. So he will send that duplicate address detection message, and that's a multicast message. So this duplicate address detection message will be sent to the network, right? So if any machine is using that link local address by any chance, for example in VM or any MAC address spoofing, anyone does the address spoofing, right? They might use the same address on the network than in link local. So that's why the new machine will send a multicast message into the network, and by sending the multicast, it will try to see whether the same address has been used it or not. If not been used, no one has replied on that multicast, then the machine knows, yes, this address is unique. So it will build its own address. Then after that, it will try to know or try to discover its global address. So when they send that duplicate address detection message, the messages that we classify, we call it neighbor solicitation message. That message, the new machine who is coming out, they will send the multicast to the network. That's what we call neighbor solicitation message. And if any machine is using the same address, they will send a reply, right? We call neighbor advertisement message, or NA, right? So when the neighbor advertisement message comes, then there is a problem. So normally it's well expected, there is no reply comes back, so that's why the address is unique. But in any case, if the reply comes, then the machine will generate a protocol error message like IPv4 address duplication, right? Okay. Then at the second stage, what it will do, when it will have is link local address, then the machine will try to send another multicast message in the network and try to see whether there is any router. And if there is any router, this router will give the global address to the machine, and by having the global address, it will try to communicate outside the LAN, right? If there is no routers, no reply comes, fair enough, the machine will have only the link local. So that's what we call router advertisement message. The machine will send at the second stage, and is waiting for a router advertisement router solicitation message. So when the router solicitation message comes, that message can carry the global prefix, default gateway, and also some others. Okay. All right. Subnetting example. What are the examples that we have to subnet? For example, provider A has been allocated an IPv6 block, which is 2001 db8:/32, right? So provider A will delegate /48 block to the customers. So when it delegates /48 block to the customer, what it will do? Find the block provided to the 4 customers. So how we do the subnetting? So if it need at least 4 subnet, how many bits that it need to take to build 4 subnet? So if it take 2 bit, then it can build 4 subnet, right? 2 to the power 4. So okay. So how it can be done? You see, the first block is 2002 db 0 db8, then all 0/48. Then second one will be 1, 2, 3, and this is how you can. We'll show you the subnetting example. But in this slide, what we're trying to explain is, if you have, say, from 32 up to 48, if you have 16 bit in your subnetting, then how many subnet you can create? 16 bit you have, say 32, 48. So 48 minus 32 equal to how many? 16 bit. 16 bit, then how many subnet you can create? 2 to the power 16. 2 to the power 16 means around 65,535 new subnet that you can create. Right? That's the basic mathematics actually. Okay, now we'll have a look on subnetting example. Okay. So if we need to build a number of the 4 new subnet from this /48, how we can build that? Okay, so if we have this 48 bit means 16 plus 16, 32 plus 16, 48, right? This 48 bit we have. From there, if we need to do further subnetting, and on the further subnetting, say how many new subnet we need? We need 4 new subnets. So if we need 4 new subnet, then how many extra bit that we need to take? From 48 bit, 48, and then 2 more bit, right? 48, 49, 50. So 5 new bits. Sorry, 2 new bit. When you have 2 new bits, where are those 2 new bits? Those 2 new bits are on block 1, 2, 3, block 4. On the block 4, in here, if I draw, just a sec. Yep, I'll have a pen tools. Okay, so in here we have block 4, 1, 2, 3, 4. 4 block. On the block 4 we have got 0, 0, 0, 0. 4 binary 0, right? Sorry, 4 hexadecimal 0. And each hexadecimal 0 we have 4 binary bit. 1, 2, 3, 4. Like this. So what we do, we take those 2 bit for subnet. So take those 2 bit, then build your truth table. 0, 1, 0, 1, right? And then 0, 0, 1, 1. Those are the 2 new, 4 new subnets. So then leave those 0, 0 as it is. Then if you convert it to hexadecimal, then it will be 0, 0, 1, 0, 0, and 1, 0, 0, 0, 1, 1, 0, 0. So those are the 4 new subnets. So this is how you do the subnetting in IPv6. Okay. Let's have a look few more example. In this slide we have a /32 2406 6400 : /32. So from there, if we need to have, say for example, 16 new subnet. So if we need 16 new subnet, like how many binary bit we need to take? 16, like 2 to 4 bit. So 2 to the power 4 equal to 16, right? So where are those 4 bits? In this example here we have /32. So those 4 bits are actually on 3rd block. On the 3rd block we have got 4 hexadecimal digit. So in each hexadecimal digit we have 4 binary bit, right? So we take those 4 binary bit and do the subnets. So now we build the truth table. 0, 1, 0, 1, 0, 1. It goes up to 16. 0, 0, 1, 1, 0, 0, 1, 1 goes up to 16, and then 4, 0, 4, 1, then 8, 0, 8, 1. So this is how we have 16 new subnet, and then just convert them into hexadecimal. 0, 1, 2, right? This is how you have your all new subnet, and then remaining 3 hexadecimal digit. So this is how you do subnetting. Okay. All right. So that's towards the end of the presentation today. Is there any question about subnetting, about IPv6 addressing, address structure, or is it all clear? Do you have any question, by the way? Okay, if no question, then as I said, we have an URL. I'll show you here. This is the URL that you can use. Oh, the question is, we do not have any class in IPv6. No, in IPv6 there is no concept of class A, class B, and class C. There is no concept. In IPv6, only the prefix length. There is no class. Is that clear? Okay, so if no more question, then this is what the URL that you can use to give us some feedback. And as I said, your feedback is very important for us to improve our future e-learning session. Okay, so just please spare some time and give us some feedback, and then when you finish your feedback, it will redirect you to an FTP site. From that FTP site, you can download this presentation what we used today, right? Just finish the feedback, then it will take you to the FTP site. From there you can download the presentation. I'll show you the slide again. So we have our IPv6 at APNIC website. If you go to www.apnic.net and then just tap onto the community tab, and then under that you can see IPv6 at APNIC. So on that website you will see lots of useful information that can be utilized for your address deployment plan. Okay, so and we also have all sort of new technology information on that website, so it's worth having a look, right? And then afterward, if you still have any question, you can come to APNIC Helpdesk. Our Helpdesk is running from 9 AM to 9 PM in Brisbane time. Brisbane time is GMT plus 10, and we are still 9 AM to 9 PM Monday to Friday, right? You can also phone us. You can also use VoIP to contact APNIC, or you can use online chat, right? And online chat is very popular and useful. If you have any training related question, you can send email to training@apnic.net. We'll try to answer your question as quick as we can. Okay, so that's it. That's the end of the presentation. Hope the presentation will be useful for you. And yeah, please just visit that feedback URL and give us some feedback so that we can improve our future e-learning session. All right, so that's the end of the presentation for today.